Hi, I'm Josh Urban Davis from Dartmouth Discovery Lab. My slides will allegedly be here eventually. There we are. Okay. Hi, I'm Josh Urban Davis, and today I will be presenting our work on CircuitStyle, a system for peripherally reinforcing best practices in hardware computing. Let's talk about hardware computing. Novice engineers often learn how to prototype circuits by replicating tutorial circuits on breadboards. However, teaching and learning circuit prototyping is difficult for a variety of reasons, including that novice engineer circuits tend to be big, stinking, wiry messes that are very difficult to understand and even more difficult to debug. This creates frustration for novice users and can often be discouraging from them pursuing and understanding the discipline. To solve for this, we looked to software engineering and were inspired by the practice of coding styles. Examples of coding styles include type indentation, such as tabs versus spaces, naming conventions, such as camel case versus underscore, and bracket etiquette. Coding style can be thought of as good penmanship for coding. You will notice in the two slides here, the slide on the left has implemented a particular kind of coding style that makes it easier to read than the slide on the right. You might not agree with that because one thing that we discovered was that much like fashion style or graphic design style, coding style is subject to subjectivity. And often different instructors and different practices employ different style practices in their coding. But what we found regardless is that implementing coding style practices in an organization can greatly increase the readability of code as well as make the code less prone to errors. So our inquiry was quite simple. Many instructors agree that similar best practices exist for circuits and are important to learn, but rarely are they taught in formal settings due to time and attention constraints placed upon the instructor. To account for this, we conducted a design inquiry and prototyped a web interface called CircuitStyle, a peripheral behavior reinforcement system for in-person hardware computing tutorials. We devised a semi-structured interview and a series of formative studies by recruiting 5 instructors who taught electronic prototyping at various institutions, including formal primary education classrooms, makerspace workshops, and higher education. We compiled a list of best practices behaviors, which you can see a sample of here, and there are more in the paper. And we asked these instructors to rank on a Likert scale from 1 to 7 the importance of these behaviors. To give you an intuition of the kind of best practices we are referring to, I will show you a few now. One in particular that was very important to our instructors was ensure a component's polarity is correct before insertion. For any of those in the audience who have ever blown up an LED, you're very familiar with this particular pitfall. Another best practice that we discovered that was popular was avoid changing components on a breadboard whenever the board is powered, because this can be quite dangerous and you can give yourself a bit of a shock. This work builds upon existing research in the design of classroom management and learning tools, such as Maestro, which was presented previously here at UIST, circuit prototyping tools, such as trigger action circuits, and insights from teaching coding styles. Our research goals are to better understand these best practices for hardware and to examine how we can design an interface to gently encourage students to make better implementation choices when building a circuit with an instructor, without further burdening that instructor to reinforce these practices. I'll now provide you with a brief walkthrough of our web interface system, which is comprised of 3 components. First is a tutorial authoring tool for instructors. This allows instructors to author their tutorial step by step, uploading photos for each particular step. This is to encourage instructors to complete the tutorial themselves while they are authoring it, so they can take photos and identify problem spots that students might encounter. Once the tutorial has been authored, we then allow the instructor to either use our default repository of circuit-style behaviors or to author their own circuit-style behaviors. In either case, either editing or writing their own style, there are several customization aspects to writing a circuit-style behavior. This includes uploading photos of both good and poor implementations of that particular behavior, as well as a description of the behavior indicating a severity level for the behavior from low, medium, or high, and choosing a method to reinforce that behavior, such as either using a quiz, which the instructor will write, or to use peer review, which we will address later in the student section of this presentation. Once the instructor is satisfied with the repository of styles that they have authored, they may then assign these styles to particular steps where keeping that style in mind would be useful. We also provide a very crude recommendation system for assigning these styles to particular steps. We will now examine the second portion of our web interface, which is an in situ interface for instructors for in-person workshop tutorials. This is the main interface that the instructor sees during the in-person workshop tutorials. At the bottom of the screen, you will see a series of pie charts. Each one is associated with a particular circuit style, and the red and green reflects the class's overall performance at that particular behavior. At the center of the screen, you will notice the circuit diagram for the current step that the instructor is demonstrating. And on the right, you will notice a list of all of the steps in this particular tutorial that are color-coded according to the class's overall progress through the tutorial. Red, for instance, indicates that very few students are currently completing that step. Green indicates that the majority of the students in the class are completing that step. And gray indicates that no students are currently completing that step. By clicking the Style button in the top right-hand corner of the screen, the instructor is given a more granular view of the classroom's overall performance. In this grid is associated a number of cells, each one with a particular student in the class. For each student, the instructor can see the student's most recently uploaded photo for peer review, as well as a pie chart reflecting how well that student is performing on the CircuitStyle behaviors for the overall tutorial. The instructor can also provide positive reinforcement and direct feedback. The third and final element of our overall user interface is a student view for these in-person workshop tutorials. The first step after logging in is the students are asked to sort the steps of the tutorial themselves. The tutorial that the author writes, each of the steps is then randomized, and the students are asked to sort them. This is done in order to encourage students to keep in mind that there is a proper and safe procedure for implementing circuits. I return you to our earlier intuitive example of making sure all of the elements are in the breadboard before powering it. This step was designed in order to encourage these sort of behaviors. After completing the sorting step, the student is then brought to the main interface for the tutorial. On the right, you will see the current step that the student is working on, with implementation instructions as well as a photograph detailing how to complete that step. And on the left, you will see the style guide, which is color-coded according to the severity of that particular circuit style behavior and contains both good and bad examples of how to implement that particular behavior. It is collapsible as well as searchable, and the default style is always indicated by the instructor during the authoring step because it may be pertinent to this particular step. After completing each section of the tutorial, the students are asked to take a photo of their current breadboard implementation. This is then sent to other students for peer review. After the student has taken the photo and sent it to the other students, they are then presented with a photo of another student's work, as well as a good example of particular circuit style behaviors, and asked to comment on whether or not those behaviors are evident in this particular breadboard. Once the student has completed this, it is sent back to their peer to give them feedback on their performance, and they also receive feedback from their peers on their performance of these style behaviors. This is done in order to reinforce these behaviors without creating an additional cognitive load or labor burden on the instructor. To evaluate the effectiveness and usability of this system, we developed a case study with undergraduates. We recruited 11 students for a 90-minute instructor-led workshop where the students were asked to create a button-activated motor circuit. We collected a variety of information and data on the performance of these students. The instructor was asked to create the tutorial beforehand. And during the tutorial, we collected audio and video data of the students' progress through the tutorial, as well as conducted semi-structured interviews with both the participants and the instructor, and also completed entrance and exit questionnaires, including a Likert scale exit questionnaire to evaluate the overall performance and interaction with this interface. Some of our key takeaways is that glanceable awareness of students' progress was very important to our instructor. We didn't want the instructor to spend their entire time staring at a computer screen. We wanted them to engage with the students as much as possible. And using this color-coded system that was immediately recognizable allowed the instructor to see as quickly as possible where the students were and what they might be having trouble with. And this encouraged them to address these issues directly. We also wanted to supplement and not replace an in-person instructor's capabilities. We think the interaction between an instructor and a student is very, very important. And we found, much to our surprise, that the instructor commented that they found more often than not the interface helped them to go immediately to the students who needed help, and also were able to better facilitate that interaction with them. Finally, we wanted our system to have an ambient nature. It needed to sit in the background and not obstruct the student from learning, nor require the instructor to conduct additional labor in order to teach this particular kind of material. We also collected feedback from students. I should mention now that 100% of our students were able to complete the tutorial. We allotted 90 minutes for the workshop, and the students on average took 41 minutes and 16 seconds with a 9-minute and 14-second standard deviation. So in about half the time what we allotted, they were able to complete the circuit. And we found that only 3 out of the 11 students who used the style guide and the workshop required additional assistance outside of the instructor or the interface. In summary, what we can take away from our case study is that best practices for hardware computing are important to learn, and in addition, these best practice behaviors can peripherally be reinforced with carefully designed software that doesn't create an additional burden on the instructor by allowing students to better reinforce the material through peer review with each other. This work is very preliminary and provides many opportunities for future work in this area of inquiry. One thing is scaling peer review would be very useful. We found that students often, when they were performing peer review, would turn to their neighbor and ask them what they thought of the particular circuit that they were working on. And this is something we really think should be encouraged, not discouraged by our particular system. So adjustments to our system could help to account and encourage this sort of in-person peer interaction, and our system in our current implementation might be better suited for larger classroom sizes. In addition, we wanted to account for varying skill levels with our students. Some students expressed insecurity in the feedback they were providing their peers since they were novices, they had never done this before, and so they were kind of worried that the feedback they were giving was not very good. So future implementations and adjustments in this particular kind of work could calibrate the system based on the student's knowledge and previous experience, allowing more experienced students to mentor lesser experienced students. And finally, AR-based approaches could reduce the code switching required for a student to go from the computer screen to the hardware prototype, and could instead present the entire interface in an augmented reality glass in front of them. I'd like to quickly take this opportunity to thank the UIST Organizing Committee as well as our session chair, Anna Glassman. And I would also like to thank my collaborators Xing-Dong and Xing-Dong Yang from Dartmouth Discovery Lab, as well as Parmit Chilana from Simon Fraser. I'd also like to thank our workshop instructor, the interns, the participants, and everyone who made this particular project possible. I think I somehow ended well under time. That never happened during the rehearsal. Great. So I now would be happy to take your questions. You may also ask me by email or on Twitter. Thank you so much.
So I'd like to ask whether you see this more as kind of a checklist manifesto that people are going to go forward making better designs with, or if you see it more as something to be drilled into students' heads such that as they go off into the world, it's internalized and then continue to follow the best practices, and these are the training wheels that you eventually expect to take off their bike. That's
an interesting question. I love the phrase checklist manifesto. But Since style behaviors in coding and in programming in particular vary from organization to organization, we have a feeling that hardware style behaviors as well will vary from organization to organization. And so the goal overall is to just make sure that kind of gently encourage students to pay attention to these sort of things. And so when they do go out into these organizations, they can implement these circuits in a cleaner way that's more readable by their peers and easier for them to figure out what's wrong when something does break.
Excellent.
I'm going to assume I just explained everything very well.
You did. Very.
Hey. Sorry, I'll ask a really obvious question. How far would you say this scales? Like, how much did the instructor like actively work with the students? Like, could this scale to a hardware MOOC or something? Or
yeah, that's a really interesting question. Yeah, the instructor worked. We really did want to encourage the instructor and student like in-person interaction because we found that we think that's extremely valuable, and especially learning these kind of fundamental skills. We think it could definitely scale to larger classrooms, but the instructor really was we were worried that the instructor was going to spend the entire time staring at their computer screen and not helping students, and we found that they actually didn't really do that very much at all. He would kind of come by on occasion, glance at the screen, and then go straight off to another student to like help them work. And this was kind of one of the goals of our design decisions, was to make sure that the instructor was spending as much time interacting with the students as possible. But seeing how well it would scale to a 200-person intro class would definitely be an interesting thing to examine in future work. Thank you for the question.
If we don't have any other, I think we have a third question. We must. Yes.
Thanks. Great talk. Awesome stuff you got there.
Thank you.
I'm David from University of Calgary. One question that I have is in terms of scale, not in terms of people, but in terms of the types of hardware prototypes that you make. Because I think one big challenge that I've noticed, especially with Arduino type of stuff, is that it's really easy to get one small thing to work, but once you build a larger object, then it becomes this mess. So I was wondering how this could go into more complex objects. And whether you've seen that or looked into that?
Yeah, totally. That's a great question. And we actually addressed this in our limitation section in the paper. And I was going to address it in the limitation section here and took it out last night. But we found that one of the features that we had was breaking it down into particular sections and subsections to be completed. So we can take a large circuit and break it down into smaller and smaller and smaller components, and then peer review those smaller components as opposed to looking at and trying to reinforce these practices in a huge, huge system that does something big and complicated. And our circuit was very, very simple. All it was push a button, motor turns on. And in the future, it would be really, really useful to actually understand if this is scalable to these larger, more complex circuits without creating one of the messes that I showed at the beginning of the talk.
Thanks.
Thank you.
Wonderful. Thank you again.
Thank you.
So I have two announcements. The first is that please do, as you're watching these presentations, both in this session and beyond, indicate which ones you think